contributed talk in this section is Tanahashi-san, also from Recruit Communications. He's going to talk about QBoost.
Okay. Good evening. My name is Kotaro Tanahashi from Recruit Communications, and it's a pleasure to be here today to share with you my work on quantum annealing for feature selection. And I'd be very happy to take any questions you might have at the end of my short presentations. So before I get into details, let me share a quick overview of our main results and direction. Our work is focused on feature selection, and we ultimately succeeded in achieving high precision with a low number of features. And this work is a little different approach for feature selection from QX branch, in that this is nonlinear model. And so what exactly is feature selection, and how is it so important? The image on the left represents a typical data structure of the internet user's data. And you can see that data contain each user's browser details and access patterns and more. And the columns represent features, while each row corresponds to an individual user. And features in orange are selected features, while the ones in blue are not. And feature selection is an important method in machine learning, and it selects relevant features in data for regression problems. And in the example of internet users' data, feature can include the user's sex, browser type, or OS type, among others. In a regression problem, only a few of these features are important, and feature selection can identify them. And also selected features like these can be considered as important factors which might be useful to consider in business or scientific data analysis. And also by using feature selection, input data can be reduced, and by consequence, computational cost is also lowered. So feature selection by nature is incredibly hard when considering all possible combinations of features. This image represents how feature selection is difficult to solve as the number of combinations increases in exponential manner. And this kind of problem is known to be an NP-hard problem. And as an example, given a dimension count of only 20, there are approximately 1 million combinations of features. And this extends out exponentially, meaning that a feature count of 100 results in the number of features being 1.2 times 10 to the 30, and incredibly computationally intensive. Now, I'd like to quickly look at some of the current state-of-the-art algorithms for feature selection and the problems they suffer from. In short, they avoid dealing with combinatorial problems and are simply approximate method. There are currently two famous feature selection methods in the regression problem, each with their own downsides. And L1 regularized logistic regression here is simple and fast, but it fails to make a good prediction when it's applied to nonlinear data. And on the other hand, feature selection by random forest has good prediction ability, but it can select redundant features because features are selected in a greedy way. Both methods suffered because they're kind of an approximate method, and they avoid calculating the combinations of features. So why did we attack this problem? Currently, there exists no practical feature selection method that takes into account the combinations of features. Yet quantum annealing is expected to find the global optima in combinatorial problems, so it seems suitable for feature selection problems. And no such method has so far been developed. And our contribution was to formulate feature selection problem as a combinatorial problem based on QBoost, and we developed a method to transform this problem into QUBO. that's being solvable by quantum annealing hardware. And the ultimate goal of our work is to build a strong classifier with as few features as possible through optimizations of quantum annealing hardware. And in this slide, I'd like to demonstrate how to formulate a feature selection problems. The crucial element is to select weak classifiers instead of selection features directly. We create a new feature space by using weak classifiers to capture nonlinear interactions between features in data. Now, by using weak classifiers, we can express the training loss and the number of features at the same time by the binary defined variable W. And some points to note that, firstly, finding the optimal combinations directly is difficult. And also, we borrowed the idea of using weak classifiers from QBoost. And further, quantum annealing for feature selection, or QFS for short, select the optimal combinations of weak classifiers so the training loss and the number of features are minimized. And finally, each weak classifier is associated to some data, some features in data. So once weak classifiers are selected, and then selected features are also automatically determined at the same time. So the objective function of the QFS is expressed with three terms. The first term is training loss, and the second term being L0 norm of weak classifiers, and the third term is number of features. And by reducing the training loss, the prediction ability of the model becomes better. And by reducing L0 norm of weak classifiers, the model becomes sparser. And by reducing the number of features, only necessary features are selected. And as you can clearly see, the first and second term are the same as that of QBoost. So, and thus can easily be formulated as QBO, which as a form of optimization problem can easily be mapped on quantum annealing hardware. So moving on to how we calculate the number of features. The formulation of feature selection term is non-trivial. And I can demonstrate this with a simple example. Let's assume, as in this example, that there are 4 features and 3 weak classifiers. And the association of the weak classifiers and the features is expressed like this. And when W is 110, then the selected features is F1, and F3, and F4. So the total number of features is 3. But however, the question is how to represent the number of features in QBO. The solution is that the selection of feature can be expressed by the logical sum of W containing this feature. So again, let's take a simple example shown on the left. In this case, the number of features is expressed as such here. And here we introduced W bar and the ancillary variables to reduce higher order interactions. And in general, the number of features is expressed by like this. And however, we need to introduce a penalty function for W bar and the ancillary variables here. So that deal with how to represent the number of features in QBO. Let's take a look at the specific formula of feature selection terms here. The feature selection terms are composed of the logical sum of W and the penalty functions. And finally, we can derive QBO formulations of feature selection terms. So as a quick reference, here are the parameters of the hardware we use. And we use D-Wave 2X for QFS optimization. And the latest model at the time of the test, the QUBO was mapped to the hardware using random search algorithm. The annealing time was experimentally determined at 20 microseconds. And finally, during one optimization, we performed 100 annealing repetitions. So looking at the evaluation of the model, the feature selection model needs training with training data and AUC loss with test data calculated. A good feature selection model should low AUC loss even with a small number of features. And we can simply define its efficacy as feature selection ability equals low AUC loss with as few features as possible. So how does QFS perform in real-world applications? In this chart, we can see a comparisons of 3 different models. The x-axis represents a number of features, with smaller being better. And the y-axis showing AUC loss, with smaller being better again. And the optimal result is in the lower left corner. And we confirmed that QFS is better than other methods. It should be noted that AUC loss is the more important criteria than number of features. And we applied QFS to further real-world datasets, and we chose online ad data here. And it's collected by our real advertising system because we wanted to confirm whether the algorithm is practical and applicable to the real business scenario. And online advertising was the original driver of our research, so it served as a good evaluation of the algorithm's efficacy. And as before, the charts show a number of features across the x-axis and AUC loss on the y, with lower and further left being the optimal result. And each chart shows performance for different types of datasets, and we compared QFS in red here, and random forest feature selection in green, and logistic regression in blue. In all dataset cases, QFS outperformed other methods. Now, as an interesting note, QFS requires only 10% of the weak classifiers needed by random forest. So it can be considered to be 10 times faster in prediction tasks. And tab search is a kind of global optimization algorithm that is known to solve combinatorial problems efficiently, so it can be an alternative to D-Wave as a solver. So we compare the results of QFS with D-Wave to QFS with tab. The results of D-Wave show comparable AUC loss while using a lower number of features, which suggests that the optimization performance of D-Wave is better. And looking back again at comparisons with tab across different datasets, we can see QFS in red outperforming tab in black across all cases. So in conclusion, we formulated feature selection as a combinatorial problems based on QBoost and developed a method to transform this problem into QUBO. We applied QFS to real-world data and confirmed better results than those of the other state-of-the-art methods. And this work was done in collaboration with Shinichi Takayanagi from Recruit Communications and Shu Tanaka from Waseda University. And thank you very much for your time today. And at this time, I'd be happy to take any questions. Thank you.
Thank you, Tom. Question?
I was tempted to ask this a related question in the previous talk, but now I have more energy. So it seems as though you're adding the number of features as a penalty term, and you made the comment several times that you want the lowest number of features. But shouldn't you really be using something like the Aki-Iki information criteria to decide which is the best model, which would then naturally make you help you pick the right features?
Aki-Eki?
Yes. So this is well known, and especially in linear regression, in terms of how many model parameters you want to use. There's a penalty for each time you add a, and
Akaike, okay. So
thank you.
Akaike,
Thank you.
yeah.
Sorry.
He's a Japanese.
That's actually why I didn't bring it up earlier, because I didn't know how to pronounce it.
And so can I ask you a question again, please?
Yeah.
And sorry, what was the last part?
No. But so that it's not just the number of features, but it's a
Okay. Number
relationship
of the parameters.
that has to do the information criteria takes
Okay.
the degrees of freedom that you're
Yeah.
adding into your model, and it gives you the most likely model that is representative of your data.
Okay.
Given the fact that it essentially penalizes you in a nonlinear way for the extra terms in your model, and it also naturally incorporates whatever loss function you're using to give you the most likely
Yeah.
model.
So, but at this time, we didn't evaluate our model with such criteria. So,
Well, but sometimes your model is the number of features.
yeah, but maybe in Akaike criteria, the number of the parameters is penalized, right?
Yes.
So, but this time we used weak classifiers, so there actually is so many parameters there. Yeah. So that's why we didn't evaluate our model with such criteria. So yeah, but it has to be related. But yeah.
All right.
Does that answer your question?
Yes.
Thank you. And any others?
Sorry, Taboo seems to be doing worse than D-Wave. Is that because it's not finding the ground states as often, or is it because it's always finding the ground states?
No, just we didn't make sure that the solution was the ground state. Yeah. So when I map the problem into the hardware, and then the logical qubits and the physical qubits are totally different, because some variable has to be in a chain. So some solutions from the hardware is actually some breaks the constraints or the chain constraints, but some broken solution can be a good solution for the logical problem. So even though the hardware can't find the ground state, the solutions from D-Wave solver can be the good candidate for our problem. Yeah.
Is it? My question is it necessary to see the ground states for this algorithm to work?
No, I don't think so. Yeah. Thank you for the question.
Any other question?
Maybe you were hungry, so yeah, let's go to the banquet.
Let's thank our speaker again.